Hi, today we'll discuss one more application of op-amp, that is O- op-amp as non-inverting amplifier. So this is the circuit diagram for non-inverting amplifier. So what we are doing is we are giving input, that is Vi, to the non-inverting terminal of the op-amp. At the same time we are grounding the inverting terminal via resistance R1, and also we have connected one feedback resistance RF between inverting and output terminals. So next what happens is, since op amp has got very high input resistance, so it will not allow any current to enter into the op amp. So whatever the current, that is I1 flowing through R1, that will not enter into the op amp. So all this I1 will move towards feedback resistance RF. So I can write I1 equal to IF. So next what I'm doing is I'm expressing current in terms of voltage and resistance. Okay. So I1 means it is the current that flows through R1, and IF means it is the current that flows through RF. So R1 is connected between ground and V2. Similarly, RF is connected between V2 and V0. So I can express I1 in terms of 0, V2 and R1. So I'm writing it as, so I1 means it is a potential difference. It means 0 minus V2 by R1. So same thing I have written over here, 0 minus V2 by R1. Similarly, uh, IF means I need to take the, see, IF means it flows through RF. So RF is connected between V2 and V0. So I am supposed to take a potential difference between V2 and V0. So I am writing it as V2 minus V0 by RF. Okay. So this I am calling it as equation number A. So next is we have two terminals here, V1 and V2. So at V1 I can write Vi, means I can expect Vi at terminal V1. Okay. Same thing I written here. And V1 equal to V2. V1 equal to V2 is the virtual ground concept. So I can write V2 equal to Vi. I am calling it as equation number 2. Next what I am doing is I am substituting equation number 2 in equation number A. Means in equation number A, wherever V2 is there, I am replacing this V2 by Vi. Then I'll be getting this equation, minus Vi by R1 equal to Vi minus V0 by RF. So next is I'm just simplifying this, means I want expression for V0. So V0 by RF equal to Vi by RF plus Vi by R1. So next again I'll be simplifying for V0. Then after simplifying I'll be left with AF equal to V0 by Vi equal to 1 plus RF by R1. So this is the final expression in terms of closed loop gain, that is AF. So next we have one more application, that is op-amp as voltage follower. Op-amp as voltage follower means, so first we'll see what do we mean by voltage follower. Voltage follower means, say at the input side, say I'm giving around 2 volts, means at the output side I'm supposed to get the same 2 volts, means your output will follow the input. So in this diagram it looks a bit different. So input Vi is being given to the non-inverting terminal of the op-amp. At the same time I'm connecting inverting terminal directly to the output without any feedback resistance. Now what happens is I can write V1 equal to Vi, because input Vi is given to the non-inverting terminal. I can expect same Vi at terminal V1. So I have written V1 equal to Vi. So I am calling it as equation number 1. So we have one virtual ground concept, that is V1 equal to V2. So whatever the voltage I am getting at V1, the same will appear at V2. So V1 equal to V2. So that is a virtual ground. So I can write V2 equal to Vi. Means at V2 I'm supposed to get the same voltage as V1 gets. So I can write V2 equal to Vi. So I am calling it as equation number 2. Okay. So next what we need to check is, see, the inverting terminal is directly connected to the output. So I can write V naught equal to V2 because they have shorted. So V naught equal to V2 because they are directly connected. So substituting equation number 2 in equation number 3 means V2 I am replacing by Vi. So I can write V naught equal to Vi. So whatever the input I am giving, the same will appear at the output side. So if I take the gain, so gain I am supposed to get it as 1. So this is the voltage follower, means the output voltage will follow the input voltage.